You will walk away from today's video with this. This is the schematic document for the embedded systems project that you and I will be completing as part of a video series. Not only that, I'm going to take you through every single design decision that was made on the way to creating this so you can understand why things are done, not just how they are done. I want to start off with what this tutorial is intended to be and what it is not intended to be. It is not intended to be a tutorial that you blindly follow along, copy and pasting everything that I'm doing and end up with something you have no idea or understanding of, like a lot of coding tutorials out there. I am going to be going through and thoroughly explaining every design decision that I make, and what I want you to do is think about why that decision was important, what trade-offs were made because of that decision, and how you could apply that in a more broad context. This is an example of embedded systems design on an example project. What I want you to do is take the concepts that I'm trying to convey in this video, isolate them from the project, okay? The project doesn't matter. I want you to learn how to make these design decisions in your own projects, in your own designs, because that's actually what's important. This is also not a tutorial that will in-depth teach you the electronics design tools. I'm going to be using KiCad in this video, but it is not a tutorial on how to use KiCad. There are plenty of them out there on YouTube, and me doing one adds no value to the scene. What I want to do is show you how to use the tools in a meaningful way. So what exactly is this project? Well, this is Silly-Scope, an oscilloscope that nobody would or ever should use. The reason for that is because it's an introductory project, its scope is going to be quite limited in terms of what it can do, but it's still going to be pretty fun and teach us a lot of good fundamentals. Now, you might remember an oscilloscope is something I talked about in my previous video where I introduced 3 embedded projects that students did at a real university. We're going to be going through the second one because personally I believe this one is super valuable for teaching you the fundamentals of electronics and electronic design. Now that we know what our project is, we come to the first important design step, which is taking the abstract idea of an oscilloscope and actually mapping it out into high-level substructures and components. The reason we do this is because it takes our just random idea and we say, okay, these are the requirements, this is what features it needs to have, this is what it has to do, and it actually breaks that up and we need to identify how that's actually going to happen. So let's go with our oscilloscope over here. The first thing we notice about our oscilloscope is this big, beautiful display. So naturally, our oscilloscope project will also require a big, beautiful display. And I want you to take your project idea and do the same process. So your project idea, you want to be able to do this and this and this and this. What components are actually required to make that happen? Let's keep going. The next thing we notice are these 4 channel connectors down here, 1, 2, 3, and 4. Now, of course, this is the line that our signal input is going to come in. So of course, our oscilloscope is going to need these as well. And we can decide on how many channels and how many connectors we're going to want. We also have this channel selection button, channel enable button here. And that's important, right? If we're going to have multiple channels. So we might want to incorporate some buttons into our design. We've also got these knobs for the scale controls. Maybe we also want to do that as well. We've got this run and stop button here for starting and stopping the signal display updates. And we have a USB connection down here where we can save recordings to a USB drive. Finally, and arguably the most important component of all, is an analog to digital converter. So of course, our oscilloscope is operating in the analog domain, but in order for our microcontroller to display and record the information, it needs to be converted to the digital domain. So of course, we're going to need an analog to digital converter. This is going to make up the core of our oscilloscope function. These are all really useful and really important things that our project might want. And you can sort of see the process I'm going through here, where I'm taking the abstract idea of an oscilloscope and breaking it down into components we can add to our design that will actually make the functionality happen. Now that we have a vague idea of what the project is going to look like, we have to define the requirements and the scope. And of course, these are going to change as the design progresses, but they give us an initial target that we're going to aim for. Because of course, the initial design is going to have problems. Of course, as the project progresses, we're going to add to the scope or remove from the scope, you know, like this would be nice to have, or we can't technically feasibly achieve this with the current direction. This is called iterative design, and you're going to see iterative design throughout this video series. The key takeaway for the moment is that I have defined my hardware requirements in red and my firmware requirements in pink. Let's go through the list. The first thing is a hardware requirement. I want to have 2 channels. I need to have 2 physical connectors that I can attach oscilloscope leads to and probe my channels. The next thing is a hardware requirement as well. I need a graphic display And the firmware requirement is it has to show one channel. So I have to code my firmware such that on the graphic display, which is a hardware thing, we've got to have one on there, we can show one channel at a time. The next thing is a hardware requirement. I want to have a 0 to 3.3 volt range. Now the reason I have done this is to keep this introductory project simple. You can add an analog stage to our input pipeline before it reaches the ADC to add offsets or to scale higher voltages. The reason we've done this is because our little ADC chip, it can't take infinite voltage, all right? And it certainly can't take negative voltage without assistance. So what we have to do is limit our input range to 0 to 3.3 volts for now. We could add an analog stage with op amps if we want to shift negative voltages up or scale large voltages down. But this is a thing for a future iteration of the design, and this is what I'm talking about, right? For now, we're keeping things simple and accepting only this 0 to 3.3 volt range. Next, I need it to be accurate to 500 kilohertz. Why is this a hardware requirement? Well, the ADC that we are going to be using needs to be able to provide a sample rate of this. Now, you guys might have heard of the Nyquist rate. That means that to avoid aliasing, we need to sample at a rate of 2f max. That is fine for getting the gist of a signal, I suppose, but in order to display a high resolution signal, we're going to need a bit better than that, and I'm going to display a graphic up on screen that illustrates this. Ideally, I kind of want to aim for at least 10 points per signal period. So in this case, we have to be operating or sampling at 10 times this rate in order to achieve that. The next thing is listed as both a hardware and a firmware requirement because it kind of is. Data streaming and logging to the PC. Of course, I want to be able to record signal sessions and log them to a PC and potentially even display the other channel, because remember we can only show one channel on the LCD. I could potentially show that other channel on the PC if I'm streaming the data over in real time. So what that's going to look like is a little USB connector on our device, and we're going to need some PC software that receives data and logs it to like a CSV or something like this. So this is both a hardware requirement because we need a USB connector on there, and a firmware requirement because we have to implement some kind of data streaming and logging protocol. The next thing I want to do is be small form factor. Okay, this is why I've selected two channels for this. I think having a small form factor kind of signal analysis device would be pretty cool. It's definitely no logic analyzer or proper oscilloscope, but keeping this thing small form factor would add some value to the project, so I want to try and make it as small as possible. How small can we make it? I actually don't know at this stage. I just know that that is something I want to have, and we can define that later on as we get a better idea of how this project is going to come together, and that, along with everything else I've been showing you, is this iterative design process. Next, I want to have buttons, which are a hardware requirement. I need physical push buttons on there for channel activation. So just like our oscilloscope examples we were looking at, we need to be able to push buttons to turn channels on and off. We also need a button, that's another hardware requirement, with the firmware requirement of it needs to start or stop recording. So for example, it could start or stop the data streaming to the PC I was talking about just before. Next, I need LED indicators. This is a hardware requirement. I've got to have LEDs on the board for power, channel activity, recording, etc. So this is implemented in firmware, like what those LEDs are actually used for. And these are the initial requirements of my system. Without further ado, let's get designing the hardware. The next thing I want you to do is open up a spreadsheeting application and lay it out kind of like this. This is a bill of materials. You can think of it as a shopping list for all of the electronic components that we need to construct the hardware of the device. Also, I want you to get up the website of your favorite electronics manufacturer. At least here in Australia, the main ones we use are usually Digikey or Mouser, but it may vary for your country. Choosing a microcontroller is one of the most important decisions you make about your project, and I'm going to make a completely separate video detailing how to decide on which microcontroller to use, because I think that will be much more useful than ham-fisting it into this particular video. But I'm going to briefly go over the reasons why I chose this particular one right now. I'm going to be straight up with you guys. The main reason I chose this one is because I have a dev board of it lying around. This is a STM32L432 dev board. I have one of those lying around, but there are technical reasons as well, which I'll briefly cover right now. First off, They are very small. This particular one is really small. It is 32 UFQ-FPN package. It's a very small chip, and that fits my small scope requirement. The reason why I went with an STM32 microcontroller is also because this is an introductory tutorial for you guys. I want to show you how to use the STM32 Cube ecosystem because it is a really powerful code generation utility and we use it all the time in industry. So I want to give you an introduction to that. That's why I chose an STM32 microcontroller. Additionally, this particular microcontroller has an ADC built in. So let me see if I can find that here. We have a 12-bit ADC at 5 megasamples per second. So think about that number, 5 megasamples per second. That is 10 times our 500 kilohertz rate. So technically this should, in a perfect world, work out just perfectly. This is also described as an ultra low power chip. This is important for us because of our small scope. We can add battery power as a power source later on down the line. And for that, we'll want to use an ultra low power chip maybe in advance so that that's an easy transition for us. Now, you'll notice that I didn't add battery power in the previous section. That's because I'm adding battery power in as a later design iteration we can do somewhere down the line after the first prototype. But I'm making this decision now knowing that that could be a possibility in the future, so we want to use a low power chip. You'll notice it also has support for USB, which is essential because we want that data streaming functionality. Now that we've decided on this, I can go ahead and add it to our BOM. You'll see I put the part number in here, the description here, the manufacturer, the package, the designator. This can change depending on how we mess with our schematics, so just keep that in mind. The quantity that we're going to need, the price, this is in Australian dollars by the way, and the real price, which is the quantity times the unit price. And of course, a link to the URL where we can buy this component from. So we're going to fill this out as we find out what else we need. Open up KiCad, start a new project, and head on over to the schematic editor. We're going to start with a completely blank schematic. So what I want you to do is go on over to the page where we have our component, and most providers will give you this little models tab right here. So if we go on over to the models, you'll notice we have three things available to us. We have the symbol, the footprint, and the 3D model. If you're not familiar with these, I'll briefly tell you what they are. The symbol is what's going to go on our electronic schematic. The schematic is the electrical representation of what's going on. You might have seen like a PCB layout, all right? A PCB layout and a schematic, these are two different things. The schematic, it refers to how electrically everything is connected. The PCB is the physical manifestation of that, where we actually put the thing on a circuit board, place all of the individual components with their real sizes and their real layouts, and we do the routing all like that. The schematic is the pure electrical representation, and it's an important first step so that when we do our PCB design, we know how everything should wire together. The footprint is what I was referring to just before. So the footprint is this physical representation of our component. It's what it will actually be when it's placed on our PCB. And the 3D model is what we can use in a lot of designers, like Altium, for instance, will have a 3D model where you can actually place these components and see what your PCB is going to look like. Go ahead and download with select download format. And for me, I'm going to choose KiCad V6, of course, because that's what I'm using. If you prefer to use something else, go ahead and do that. And then just hit download. Go ahead and place that on the schematic. Like I said before, this isn't a tutorial on how to use the tool, so I assume you already know how to import the symbol that you've just downloaded, and just place it any way you like. Digikey and Mouser do have a selection of displays, but oftentimes I find it's a bit limited, not really what I'm looking for, or they're a little bit on the expensive side, so I also use this distributor here. This is Buy Display. Now be aware this is a Chinese distributor, so shipping times to your location will probably be a little bit poor compared to Digikey or Mouser. Let's go ahead and look at their product selection. So I'm interested in graphic LCD displays. Of course, they sell a variety, including character LCD displays, which you've probably seen in Arduino tutorials before, but we want to display full-on graphics, custom graphics. And so we're looking for these graphic LCD displays, and I'm going to have a look at the modules. You'll notice right off the bat there are some that we won't be interested in, like these sort of more slimmer profile ones. They're not going to be very good for displaying our captured signal, which is what our oscilloscope is all about. We're more likely to be wanting ones like this with this kind of aspect ratio. I want a SPI interface. Because our microcontroller is quite small and it doesn't have that many pins, we don't really have the budget for an 8-bit parallel interface, so we're going to use SPI for that. Also, I want one with a backlight, which we can select here as well, so backlight color. And this one here looks like an excellent fit. This is a 2.8 inch, so pretty small. It's got a white backlight, which is going to look pretty sharp. It's 192 by 96, so I think that gives us quite a lot of room to play with. You can see here it's detailed enough for this picture of a guy's face, so I think it's going to be good enough to draw our received signals for our oscilloscope. And it uses the ST75256 controller. So guys, it's important when you're choosing a display, there are two things to consider. The first is this panel. So this panel module is actually not the same thing as the controller. You can mix and match panels and controllers. So what this is saying here is we've got a white 192 by 96 panel that is using this controller here. So this controller is what we're actually going to be talking to over 3-wire SPI. And you can see down here, if we look at the datasheets, there's a datasheet here, which is for the panel, like the panel module, which is going to include the pin interface, the sizing and things like this. But you'll also notice there is a much more detailed ST75256, which is the datasheet for the driver. And you can see here we've got some timing diagrams and things like this, which is going to be important when we write our communication driver. Another thing I really like about BiDisplay is that they give code examples for the drivers. Now, I have found the code quality of these examples to be quite poor, but what it is good at is giving you a code-based illustration of these timing diagrams so that we can write our own communications library kind of based around this, but with a little bit better code quality. And if you don't know how to write your own communications library based on this BiDisplay example code, well, I have a full tutorial where I go through and do it for an e-paper display that I used in a different project. So this is a really good introduction to embedded graphics. You'll learn about frame buffers, bitmaps, vectors, fonts, and things like this, and also how to write your own communications library, which is going to be important for our oscilloscope project, but we'll get to that later on. The only thing about BiDisplay is that they don't give you a footprint or a schematic. Footprint doesn't really matter because this is a breakout module, but in terms of the symbol for our schematic, that's going to be important. I've done one up here with KiCad's symbol editor. Again, like I said, this isn't a tutorial on how to use KiCad, so I assume that you already know how to do this. We've got two big components here. We've got our microcontroller and our LCD. Let's start wiring some things up. Now, the first thing that we're going to notice is there's no power. We don't have any power in this design yet. And this is where the concept of power rails comes in, guys. So a power rail, you can think of it as essentially just a line that you can draw power from. So for example, with this VDD here and VDD1 and VDD AREF, these all need to be connected to a power rail. The same thing goes for LEDA and VDD. And the number of voltage rails we need is going to be dependent on the differing voltages required by our components. So for example, if this MCU over here needs 3.3 volts and this LCD backlight requires 5 volts, then we'll need a 3.3 volt and a 5 volt power rail in our design. Fortunately for us, as we'll see in the datasheet, we only need one power rail in this design because this guy works off 3.3 volts and this guy works off 3.3 volts. But let's go ahead and show you where you actually find this kind of information. First, let's check out the display that we just chose. So if we scroll down and click on the module datasheet, you'll notice in the sidebar we have a section called electrical specification, and one of these headings is called absolute maximum ratings. So if you come over here, you'll see that the power supply for the logic, now this is the controller chip that we were just talking about. Remember I told you there's a difference between the controller chip and the panel. You'll see that the maximum voltage this can take is 4 volts. So the power supply for the LCD, that's the backlight, or for the panel module, the maximum this can take is 19 volts. So we have to be careful not to be exceeding these values. Now if you look down here, we can see the typical characteristic. So the power supply for the LCM, that's VDD to VSS, is typically 3.3 volts, and so we'll aim to have a 3.3 volt power rail, but we do have tolerance to go a little bit below or a little bit above depending on the other components in our system. If we take a look at our little microcontroller, you can see immediately there's a 1.71 to 3.6 volt power supply, so that 3.3 volts is looking pretty fine. We can also see there's an absolute max rating section over here as well, and you'll see that the absolute max of VDDX to VSS is 4 volts. We don't really want to be hitting that, so as long as we stay in that range of 1.7 to 3.6, we're going to be chilling. So let's just add one 3.3 volt rail to our design. Whoa, 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 buddy. Hold your horses right there. We've already made a critical mistake. So guys, all I've done is wired up 3.3 volts to our display and our microcontroller. What could be so wrong about this? Oh, my sweet summer child. Let me tell you what's wrong with this. We have forgotten to include decoupling capacitors. These are really important. I'm not going to go on a big spiel about how they work. Dave from EEV blog has an excellent video on it, so I'll link that in the description. But essentially what a decoupling capacitor is, as our integrated circuit switches, so turns on and off, this is going to create noise on our input voltage rail that we want to avoid by adding a local power supply to help stabilize it when the voltage ducks due to the transistors switching on and off. So that sounds really complicated, but actually we have a nice little application note from ST that essentially tells us how to do this. So what I'm looking at here, guys, is application note 4555, getting started with STM32L4 series hardware development. If we come down here to the recommendations section, you'll see that we have a decoupling section where it tells us what we want to be doing. So you can see here, we want to add this decoupling capacitor to VDD and VSS as close to the chip as possible. You'll notice over here in the recommendations section for decoupling, you'll see each power supply pair, so that's VDD and VSS, should be decoupled with ceramic capacitors of 100 nanofarads, that's 0.1 micro, and a tantalum or ceramic capacitor of around 10 microfarads connected in parallel on the devices. What that means in real terms, and we can see that down here with the reference design as well, is that you need one of these for every VDD VSS pair. Now you can see the decoupling capacitors are in place according to the application note, and I've also added a note of my own to say where these individual capacitors should be placed in proximity to these pins. Now if we scroll down to the bottom here, you'll note that they are connected to the VSS pairs and ground, which is as it should be. You'll notice I have not actually added a decoupling capacitor on this LCD module. Why is that? Well, if we go over to the website and we actually look at the back here, you'll note that there are some capacitors already on the back of the board. This may not always be the case, so it's a good thing to just check out for yourself. We can trace from this VDD pin here that there is a capacitor C1 which is actually already decoupling VDD. So do we actually need this? We can look further into this. If you scroll down to this tutorial and example and just download it, there is a interfacing guide that already says this, and you'll notice that there are no capacitors in this thing. So I'm going to take their word for it and say we don't need it. We can always add some later if we find that we do need it, but for now I'm going to leave them out because of this. For this next part, we're going to start using STM32CubeMX to do the pin definition on our microcontroller. So go to the link in the description and download this if you haven't already. I believe you need an ST account. But anyway, once you've done that, all you want to do is go to File, New Project, and it will open up the MCU selector window where we're going to actually choose the board that we need. Up here where it says commercial part number, we can just simply start typing our MCU. So we're using the STM32L432KCU6. And once we've done that, you come over here and you can go ahead and hit Start Project. Now what STM-CubeMX is going to let us do is it's going to let us configure the hardware of the device. Previously, you might have seen people configure things on the register level, and I still genuinely believe that is really important if you haven't done anything like that before. But once you have done it and you understand how all the register stuff works, STM32CubeMX accelerates the hardware initialization by generating it all for you once you configure it in this nice graphical interface. So here we have our representation of our microcontroller, and we can change all kinds of things about it. And the first thing we can go ahead and do is go over to connectivity, and we'll select SPI 1 because remember we're talking to our LCD over SPI. So we can go ahead and change this mode. There's a lot of modes here. What we're interested in is transmit only master because we're not getting anything back from the LCD. We're only transmitting to it. You've got other modes here if you need to receive from devices as well, but for this case we're a transmit only master. And I'm going to disable the hardware NSS signal, that is hardware chip select signal, because I'm not really sure what kind of protocol this thing uses, and I'm not sure if we can just hand it all over to the SPI controller and let it just do its thing. So we're going to use software chip select for now. I may come back and change this in the future, but you can see down here, now that we've enabled it, we've got 2 pins that are assigned to SPI1. And we can actually go ahead and change these to a different one. You'll notice that if you click on one of these pins, you can get a whole list of alternate functions. You'll notice we can change other things about the SPI controller as well, like the data size and the speed. I'm going to leave these for now as default. They are incorrect. Let me get this across. They are incorrect in the default settings, as they usually are, unless you get super lucky. But right now, for our schematic, I only care about pin definitions, so I'm going to leave these for another video. Of course, one of the main reasons we chose this microcontroller is because it has an ADC on board. So let's go ahead over to analog and enable ADC1. So I'm just going to use these ones. We're going to change this to single-ended. Differential, don't worry about it too much for now. And you'll notice something crazy happened. SPI1 clock, which used to be over here on PA1, I think, has jumped because our ADC input is only available on this pin, but the clock can be on PA5 as well. So STM32CubeMX has resolved that conflict for us. Very nice of it, but be careful. This might trip you up if you are enabling and disabling things in your own design and suddenly something has jumped and you didn't anticipate it. So just be very careful when you're changing these things. Now, when we're assigning GPIO, it's a good idea to group like things together. So things that are going to go to the same place, generally speaking, you want to group them together because this is what our microcontroller layout is going to look like on the PCB. So for example, I want the chip select for the SPI to go to the LCD, of course, and so I'm going to group it with the rest of the SPI bus because that's going to go to our LCD. So I'm going to say PB0 here is probably going to be a good option for our LCD chip select, and I'm just going to enter a user label and call it LCDCS. Thinking about the other GPIO we're going to need, if you look back at our requirements, we have 3 GPIO inputs that we're going to need for these buttons, and we have a few LED indicators that are going to be outputs. So what I'm actually going to do is assign the buttons as interrupts and the LEDs as just GPIO output. There's a trap for young players doing GPIO interrupts on STM32s. If you look, we have A, we have B, and we have C. Now, if you click on this, you'll notice GPIO XTI6 for PA6, right? So each pin, like PA6, does not actually get its own dedicated interrupt line. It shares it with similarly named pins. So for example, GPIO XTI6 would be shared with PB6 right here. You can see like that. So we can only have one per thing. You can see if I change this to XTI6, we get disabled on PA6. So we have to have a dedicated pin number for each GPIO interrupt we want to do. So I'm just going to go ahead and do that. PA4 is button channel 2. PA6 is button record, and PB1 is channel 1. The reason I've grouped them with the SPI stuff is because I envision the buttons on my PCB to be underneath the LCD, so they're going to go to roughly the same place on the board. And of course, the button GPIOs are all interrupt pins, so when the user presses the button, our firmware will get an interrupt about it. Up here, I'm going to define 3 GPIO outputs for our LEDs. Just do them like so, and now I've given them user labels. Since we desire USB streaming functionality, I'm going to go ahead and enable USB. So we come down here in connectivity, enable the device, and under middleware and software packs, if you scroll down, you'll see USB device. We're going to change this to communication device class virtual COM port. This is going to give us a serial port that we can open and read data that's going to be streamed to us. I'm going to leave it unconfigured for now, but you can see USB DP and USB DM have appeared over here on PA12 and PA11. I know this is getting boring, guys, all of this same STM cube application, blah, blah, blah. We're nearly done, I promise. We need to add a debug interface to our application, otherwise we're not going to be able to program any software onto it. So if you go back over to this beautiful application note we had, which previously we used for decoupling capacitors, it's AN4555, it gives us a note about debug interfaces. There are 2 main ones really that people use. There's JTAG and SWD. We're going to use SWD because it only requires 2 GPIO wires, whereas JTAG takes up much more than that. And of course we have our small little microcontroller, which is a bit GPIO constrained on a 32 pin, so I think SWD is the better choice. So we're going to need 3 wires for this: NRST, SW clock, and SWDIO. If you head on over to System Core and you go to SYS, on debug, we can change this to serial wire, and you can see our SW clock and SWDI load up. Now, I also want a UART to be able to debug this thing on. So I'm going to go over to UART 1 under connectivity, and I'm going to go ahead and enable asynchronous mode. And you can see UART 1 RX and UART 1 TX have just lit up as well. Now that we've done a fair amount of our pin definitions, we can actually start filling out our schematic. So what I'm going to do is fill out all of the signals that our microcontroller is going to use that we've defined in STM32Cube. If you've got two monitors, this is where this really helps. These changes look really scary, but I promise guys, literally all that I've done is broken out all of these pins into little signals according to what we did in CubeMX. It's literally identical, one-to-one, and that's what we want to be doing. We've got a whole heap of blank space over here, so I'm going to go in and add some LEDs. If you remember, we need 3 of them because that was part of our requirements. And the next thing I'm going to add to these LEDs, guys, is current limiting resistors. Because here's the deal. We are going to connect these LEDs directly to our microcontroller. Now, this guy cannot draw infinite current from the GPIOs. So what we're going to have to do is limit the current that goes to all of these LEDs. Number 1, so that we don't burn out these LEDs, and number 2, so that we don't burn out our little microcontroller. Now we're in the datasheet for our little microcontroller. Underneath the absolute maximum ratings heading, if we go on over to table 19, which is current characteristics, you'll notice here we have the sum of I/O. So you look at this one, the total output current sourced by the sum of all I/Os and control pins cannot exceed 100 milliamps. So that means we cannot output more than 100 milliamps of current on all of our I/Os combined. There is a trick to calculating the resistor value that we need to use for our LED. It's this formula right here. So it says the resistor is going to be equal to the VBAT, so in our case that's our power source, which would be 3.3, minus the voltage of the LED, the forward voltage of the LED, divided by the current that you want to go through that LED. So we're going to calculate that with real LEDs. If we go on to Digikey and we go products and we go LEDs and then we go LED indication discrete, we can get an idea of what kind of forward voltages are available. Now, of course, because VLED is the lower term, we need to choose one that's lower than 3.3. So if we come over here and have a look, you'll see we can select for forward voltage typical. Now, there are so many LED forward voltages. A very common one that I've seen used is 2.1. So I'm going to go ahead and select 2.1. I've chosen this green LED to be the channel activity indicator. So if you push the button that says turn this channel on, this one is going to light up. I've chosen this one here, which is a red one, for the data streaming / recording functionality. So what I want this to do is to be blinking red on and off when we are recording or streaming data to the PC. Now this one here, this yellow one, I've selected to be the power indicator. So when our power is on and the device is not doing anything at all, I want this to be lit up just for diagnostic purposes. So I'm going to go ahead and add all of these to the bill of materials. For now, I want 6 milliamps to go through each of these LEDs. Will that be enough? I don't know. We're going to find out. That's what iterative design is all about. We could probably look through the datasheet and calculate this, but I want to show you guys some design errors. I want to make some design errors actually on purpose so you can see how we improve a product over time. Anyway, we'll see if it's good enough. Right now, I've done the calculation over here, so 3.3 minus 2.1 divided by 200 will give us 6 milliamps each, so I've gone ahead and added some 200 ohm resistors. We're going to need to go to Digikey again and find resistors for these. I want to look at this tolerance value here. So if you guys aren't aware of manufacturing tolerances, this is actually quite a big thing when you're choosing electronic components. So let's say I have a 100 ohm resistor that has a tolerance value of plus or minus 10%. That means that instead of getting exactly 100, I could get anywhere from 90 to 110 because we have a plus or minus 10% tolerance. Now, I don't want to choose a resistor that's absolute garbage, so I'm going to go for a plus or minus 5%. And we're going to go hit apply because I've done the calculation so precisely. For other applications, it doesn't matter so much. Right here, we find this one here at the start. This is from Stackpole, and it's just this 200 ohm 5%, pretty standard. So I'm going to go ahead and add this one to the bill of materials. Thought I'd give you guys an update on what the BOM is looking like when it's a little bit more filled out. You can see we've added our LEDs and our resistors. We've got a couple different packaging types, a couple different quantities, and we've got all our designators filled out like so. We're essentially just going to keep doing this until the project is done and we've got all the parts we need, and then we're just going to go ahead and order all of them and wait for them to arrive. If you remember, we also have to select decoupling capacitors for our microcontroller. We had a couple of 0.1 microfarads and one 4.7 microfarad. So to do that, we can go over to products, we go back to passives, and this time we're going to look for capacitors. If you remember from the datasheet, it said it wanted ceramic capacitors. So we're going to go ahead and select ceramic capacitors. Now, with this microcontroller, it's going to be surface mount. So we are going to select surface mount capacitors here. It doesn't matter, we're going to have to cop it. And you can see right off the bat, we've got a couple options here. Note the number at the end of these, so 0603, 0402, 0805. This refers to the size of the surface mount component. I'm going to select this 0805 so that it's easier for us to solder. But in smaller, more compact designs, if you might get this pick and placed or something like that, then these smaller capacitor sizes can be good as well. But for now, because we're going to be hand soldering this, I'm going to do the 0805s and save myself the trouble. If you've been paying attention, you've noticed something that we've left unconnected thus far, and that is this VDDA/VREF. And you'll notice that's actually quite important because we're wanting to use the internal ADC on this chip. So what we're going to do is pin this to 3v3 because, like we described in our constraints, that is the maximum of our range. We're going to pin this to 3v3, and I'm going to use another 0.1 UF capacitor to do that. Did I really just say UF? Anyway, here it is, C4 is right there, and I've made a note to put that next to VDDA, and you can see we've connected that up like this. We're missing something incredibly important at the moment, which is our power input delivery pipeline. We've decided that we're going to have a 3.3 volt rail, but where does this even come from? Well, we've already decided in our requirements that this thing is going to have a USB connection. So knowing that USB gives us 5 volts, we can start with a USB connector, and then we can add a voltage regulator to scale that down to 3.3 volts like the rest of our circuit is desiring. Here's one that I found. Now keep in mind guys, even though this is a USB-C connector, it is actually internally wired for USB 2.0, and that is really important because that is the only level of USB that our STM32 supports. You want to get a USB 2.0 connector. This is the voltage regulator that I've chosen. I've chosen it for a couple of reasons. The first reason is that it has a 3.3 volt output, which is exactly what we want. It'll step down our 5 volt USB to 3.3 volts. The second reason is because it has a current output of 1 amp. This is something you need to consider when you choose a voltage regulator, is the current limit on what it can output. So if that current limit isn't enough to power your entire circuit, sometimes you'll either need to A, get a beefier one, or B, get multiple ones, and power different components with different ones. In this case, 1 amp should be plenty for everything that we're going to be doing, so this one works just perfectly. We've imported these two, and let's go ahead and make our power delivery stage. So importantly, what we're going to do first off is connect this 3v3 to the output of this linear regulator, because that's what's going to give our entire circuit its 3.3. Now we're going to connect the input to 5 volts because of course that's what we're going to be getting from our USB connection. We are going to have to add decoupling capacitors on this guy as well. I'm going to do that according to the datasheet for this component. So you can see right here, we want a 4.7 micro on both V in to ground and also V out to ground. Here's our happy little chappy all wired up. You can see I've added decoupling capacitors on V in and V out, and then we have enable pulled up to 5 volts. So what that means is that as soon as the USB is plugged in, the output is going to be enabled. We pull up with a resistor to limit the current, and we can start wiring up our actual USB connector. Now this looks scary, but don't worry, we're not actually going to use most of these pins. So what is going to happen is V-bus is going to become our 5 volts. We're not going to connect the shield. We're going to go ground to ground. These DPs and DNs are going to combine to become our DP and DN signal down here to the MCU. And we're going to essentially just pull down CC1 and CC2, and we're not going to connect SB2 and SB1. You might be wondering about the pull downs on CC1 and CC2. Why are we pulling these down to ground, and why are we pulling them down with specifically 5.1K? Well, let's have a look at this knowledge base from Infineon to answer our question. So you can see here, we have two definitions, a downstream facing port and an upstream facing port. So a down-facing port such as a host computer exposes pull-up terminations on its CC pins, and a peripheral exposes pull-down. We are most definitely a peripheral. We want to be powered by the host computer. So what we're going to do is terminate our CC pins with pull down resistors, and you can see here the values are fixed at 5.1K. As for SPU1 and SPU2, you can see from this application note from Microchip that they are lower speed signal wires that are used for alternate mode use only. From what I understand, these are things like DisplayPort. We're not going to be using this at all, so we're going to not connect these. That's actually really cool. Now we have a full power delivery pipeline that is going to give USB power to our circuit. I'm just going to draw a little rectangle around that so we can section it off. It's always a good idea to do sections in your schematic, guys. And yes, I will clean all of this up after the video. Now we're finally going to wire up this LCD. If you remember earlier on in the video, I showed you guys this interfacing guide from ByDisplay for the 4-wire SPI interface, which is what we're going to be using. So you can see here, we're actually not using this what looks like a SPI bus, because on the datasheet for this, it says this is for a font display. We want to use the graphic display. So you can see the ones that we need to do are LED A to 3.3, blah, 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 blah. You can see we've got a data instruction selection pin. This is going to be useful for our communication protocol. That's just going to be a GPIO. We've got a reset input. That's going to be another GPIO. Chip select when low. That's going to be another GPIO. We've got these DBs tied to high, so pulled up to high, and we've got serial data input, so this is going to be MOSI, blah, 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 blah. These are pulled up to high. Now you'll notice I have deviated from the guide just a little bit. I've added pull-up resistors here, where on the guide there haven't been. Is this a mistake? Maybe. I didn't feel good about not putting them on there, and the module, I had a look at the back of it, it doesn't look like there are resistors on there. Is this a mistake? Maybe. We'll find out. Maybe ByDisplay is right, maybe they're not. Either way, this is what iterative design is all about. So other than that, we have added 2 new signals here. So these actually are signals we did not have in our design before. So what we're going to have to do is go into CubeMX, and we're going to have to allocate them. I think maybe PA3 can be the reset, and I think maybe PA2 can be LCD A0. I just want to add a quick note about sharing pull-up resistors. So you'll notice these signals here and these signals here are sharing pull-up resistors with each other. Now this is fine because they are unused. Essentially the guide just says, oh, since they're unused, you should pull them up. So that's what we're doing. In this case, it is perfectly fine for them to share pull-up resistors. If they were constantly changing or they needed to be at opposite polarities, this is probably not going to be a good idea, but because these are static, having them share the pull-up resistor is perfectly acceptable. Why have we done our push buttons like this? What is the reasoning behind it? Well, think about it. Internally, push buttons are just switches. We've got one side here that's connected to ground. The other side is pulled up to 3.3 volts via a 10K resistor. So if you think about what this signal is seeing, when the switch is open, so it's not pushed down, it's seeing this 3.3 volt pull up. But when we do push and connect this to ground, this will read 0. And I'm going to put a graph up on screen, or an image up on screen, of what this electrically looks like on an oscilloscope, and you'll be able to see what happens. And because these are set to interrupts, when we get that edge, our firmware is going to get an interrupt. So that's kind of how our push buttons are going to work. Push button switches are not hard to find on Digikey, and here I have this red one. I thought it would be fun if I had a red one for the recording and black ones for the channel select. So that's what we're going to go with. I've got one red one for the toggle recording, and I've got 2 black ones for the channel select. I'm going to go ahead and add these to the bill of materials. We just have 2 more things to do before we can call it a day. The first thing is our actual signal input stage. Now to do that, we're going to need to place some BNC connectors on the board. Thankfully, KiCad already has schematic symbols for this. All I have to do is type in axial in here, and we can use the coaxial. So I'm going to place 2 of these, of course, because we want 2 channels. Now, if you have a look at the pinout for one of these things, you'll notice that the internal component actually carries the signal, and the external component, the shielding, carries the ground. So I'm going to go ahead and wire this up on our schematic accordingly. And just for good measure, here's the component on Digikey. You can see I've got a female BNC connector jack, through hole, pretty chill. And you can see down here, this is where we've wired it up. We've got the shielding going to ground and the internal component going to our ADC. So this is amazing. We just have one more part to go, which is the debug interface, and then our schematic is functionally complete. So like I mentioned earlier, we are using SWD, and we're going to need a connector and a programmer that supports our STM32. In terms of the programmer, I've chosen to go with the ST-Link V3 Mini. It's very cheap and very widely available, and it supports SWD. Coming off the V3 Mini is a 14-pin connector, so we're going to need a 14-pin header on our schematic and on our PCB in order to accommodate this. After shopping around for a little bit, this is what we come up with. This is just a pretty typical surface mount 14-pin header that's going to fit nicely with our ST-Link V3 Mini. So I'm going to put this on the BOM, get the symbol imported, put it on our schematic, and we're going to wire up the debug interface, and we're going to finally finish this thing. So here is the pinout for our debug interface. The things that you got to take note of is that VTREF has to go to VDD, our 3.3 volts, grounds obviously have to be grounded, RST has to go to the NRST on our STM, this VCP, Virtual COM Port TX and RX, is going to go to that debug UART that I mentioned all the way back in the other section, and we're interested in SWDIO and SWCLK. The rest of these don't matter. Here's our header wired up. We're finally done. So the only thing you might have a question about is this R12 that has a value of 100. So this pin 11 is used for ground detection or like presence detection. So just trust me, it's part of the spec. You want to put this 100 ohm resistor here. Now if we come over to the STM, you'll see that we have the NRST pulled high because the programmer will pull it low via this signal right here. And the only thing we have left to do is connect this boot pin to ground. So without getting too much into the technical details, boot essentially determines where in memory the STM32 will decide to boot its application from. We're not doing anything fancy here, so really what we're just going to do is pull this to ground and call it a day. And with this, we are done. So guys, it is 5:03 a.m. in the morning. We have this design right here. I'm just going to put a rectangle around this. What I'm going to do is clean up this design, add some test points, add some fancy stuff, and then we'll get the video edited and release it to you guys. I'm really keen for this. I hope you're going to like it. I put a ton of effort into this. So yeah, let me know what you think. Cheers.